Today we're going to continue with our exploration of logarithmic functions and focusing in on the graphing part of it. Now remember that the exponential function and logarithmic function are inverses of each other. So we have f of x equals a to the x power, which is an exponential function. And the inverse of that would be f of x equals log base a of x. So this is a log. And the easiest way to tell is you see the word log. That tells us this is a logarithmic function. Now, the basic exponential function has a horizontal asymptote at y equals 0. And remember, it had an intercept at 0, y-intercept at 0, 1, and it grew quickly. And we have the domain negative infinity, infinity. The range was 0, infinity. And like I said, the y-intercept was 0, 1. Now, remember, if we think back to inverses, you switch the x and y values when you calculate an inverse. So that means the domain of a exponential would be the range of the corresponding logarithmic function, and the range of the exponential function would be the domain of the corresponding logarithmic function. And because they're inverses of each other, they could go in both directions. So if we have the information about the logarithmic function, we could go backwards and find the information about the exponential. Now, the y-intercept of exponential was 0, 1. Now, if we switch the x and y, that becomes 1, 0, but it is no longer an y-intercept, it is an x-intercept because the y value is 0. And instead of having a horizontal asymptote at y equals 0, we have a vertical asymptote at x equals 0. So what that looks like is a vertical line there. We have a y-intercept, an x-intercept at 0, 1, 0. And the graph will look like this. This is what a logarithmic function looks like. So as opposed to an exponential function that grew very fast, a logarithmic function grows very slowly. So you see, as our x values get larger, the increase is smaller and smaller. So to graph logarithmic functions, to calculate the domain we want to be greater than 0, because we can't take the log of a negative number. And if we, go back and look at our exponential function and the corresponding logarithmic one, you'll see why we can't take the log of a negative number. Because if we look at the exponential function, we can never raise a to some power and get a negative answer. For example, if we think about this, 2 to the x power equals -5 or -4, okay? There's no value of x that we could substitute in that gives us a negative value or gives us a -4 for this x value. So that's why we can't take the log of a negative number. So to find the domain, we're going to set whatever is being logged to stuff inside the log greater than 0 and solve. The range is always negative infinity, infinity. The vertical asymptote is the end point of our domain. So once we find the domain, that also tells us our vertical asymptote. Or you could find the vertical asymptote and then have that help your domain. Now to find the x-intercept, we're going to set the equation equal to 0 and solve. So that will give us our first point. And then to get our second point, our OP, we have two options. One option is to set what is being logged to the base and solve for x. This works because if we do the same base and the same other number, it equals 1. So that's one strategy. Or you can set what's being logged equal to 1, and then that will give us a point to plug in because log base b of 1 is equal to 0. Now, there's really no benefit over one or the other. Like sometimes we'll do method number 1, and sometimes we'll do method number 2, just depending on what numbers we are already given and what will give us a nice x and y value. Nice x and y value, because we want to avoid decimals and fractions as much as we can. There's going to be situations where we have them, and that's okay, but if we can avoid it, we want to have a more accurate sketch. All right, so we have f of x equals log base 6 of x minus 2. So this right here, the inside of this log, that is what's being logged. And to get the domain, we want that to be greater than 0. So we add 2 to both sides. Our domain is going to be x is greater than positive 2. So our vertical asymptote is also going to be at x equals 2. You might just say, well, isn't it just going to be the opposite of what you see inside? Yeah, it will be like that for the most part. Okay, we'll talk about those situations where it's not, because what if it was negative x minus 2? Okay, then we would have to factor out the negative and do those types of things. Then the range is always negative infinity, comma infinity. So now we have to figure out, or let's list the VA. The vertical asymptote is x equals 2. So now we have to figure out the x-intercept. So the x-intercept, we're going to set the function equal to 0. So log base 6 of x minus 2 is equal to 0. Well, in order to solve this, we have to get the log by itself. It already is by itself, but in general, we want to get the log by itself, so then we can convert this to exponent form. So now I'm going to convert it to exponent form. So 6 to the 0 power equals x minus 2. Well, 6 to the 0 power is 1. So 1 equals x minus 2. And when we add 2 to both sides, we get x is equal to 3. So this means that a point on our graph is 3, 0. Now we have to find another point. And again, we have two options. We can set the inside equal to 6 and substitute that back in because 6 is our base. Or we can set the inside equal to 1. We can set the inside equal to 1 and solve that and see if we get a new point. Now I will do, so our other point, I'll do the setting the inside equal to the base first. So x minus 2 is equal to 6. So x is equal to 8. So I'm going to substitute 8 into my original function. So f of 8 is equal to log base 6 of 8 minus 2. So you have f of 8 is equal to log base 6 of 6, which we know is equal to 1. So f of 8 is equal to 1. So our second point is 8, 1. Now, if you wanted to do it the other way and set the inside equal to 1, okay, x minus 2 is equal to 1. When we add 2 to both sides, we get x equals 3, which we already did up here. We already did that up here. We said when x is equal to 3, the y value is equal to 0. So that's not going to give us a new point. So our two values, or sorry, 2 points going to be 3 comma 0. And 8 comma 1. So that's going to be off the graph a little bit. 4, 5, 6, 7, 8 comma 1. So then the graph will look like this. Now this one looks a little bit complicated at first because we have two ln's. But the second ln here doesn't have a variable with it, so we can evaluate that. So this is really going to be f of x equals the natural log of x plus 3. Now the natural log of e to the fourth, we had talked about that earlier, that the ln, the natural log, and e, they don't cancel, but they kind of negate each other. So then it just equals our exponent, which is 4. So we have the ln of x plus 3 minus 4. And that is the one we're going to deal with. So our domain, we're going to set the inside greater to 0. So x plus 3 is greater than 0. Minus 3 from both sides, we get x is greater than negative 3. So our domain is negative 3 comma infinity. I don't think I did that over here. Yeah, we should have written this one as 2 comma infinity. Now the range is negative infinity comma infinity. And then the vertical asymptote is x is equal to negative 3. So here's our vertical asymptote. So now that minus 4 on the outside is going to play into our graphing. So we're going to find our x-intercept first. So our x-intercept, we're going to set the ln of x plus 3 minus 4 is equal to 0. Well, we know that the ln is log base e. So this can be rewritten as, if we want to write it out, log base e of x plus 3 minus 4 equals 0. So then to solve this, we have to add 4 to both sides. So then we get log base e of x plus 3 equals 4. And now we can convert this to exponent form. So we have e to the fourth equals x plus 3. Well, e to the fourth in our calculators second ln gives you e to some exponent. So e to the fourth is equal to 54.59. So we're going to round that to 0.6. 54.6 is equal to x plus 3. And then we subtract 3 from both sides, we get 51.6 is equal to x. So that means my x-intercept is 51.6 comma 0. So that's not going to fit on our graph at all. Not even close. So we're going to find our other points. And we're going to do both of them just so we get the practice of it, and it will help us with our graph. So our other point. So remember, the first one we do is we set the inside equal to 1. The inside is x plus 3. So x plus 3 is equal to 1, which means x is equal to negative 2. So then f of negative 2 is equal to the ln of negative 2 plus 3 minus 4, which is going to be the ln, or natural log of 1, minus 4. Well, the natural log of 1 is 0. Because remember, any log, no matter what the base is, if you're taking the log of 1, it is going to equal 0. So 0 minus 4, which is negative 4. So negative 2 comma negative 4 is our is our point. Now I'm going to do it the other way too, set the inside equal to the base. Well, our base is e because it's the natural log. So x plus 3 is equal to e. Remember, e is the natural number. Then we can type this into our calculator. So e minus 3. And I got the e without the exponent by pressing second and the divide button. And then minus 3. So we're going to round that to 0.3. So x equals 0.3. So now we're going to substitute that in. So f of 0.3 is equal to the ln of 0.3 plus 3 minus 4. So we get the ln of 3.3 minus 4. So then we have to take the natural log of 3.3, and we get 1.2. So we get 1.2 minus 4. So 1.2 minus 4, and we get negative 2.8. So we have 0.3 comma negative 2.8 as our point. So now we can go plot those. Negative 2 comma negative 4, and then 0.3 comma almost negative 3, so about there. So the graph will look like this. All right, now let's look at this one where we have log with no base. So let's remember, really that's log base 10 of 1 minus x plus 1. So for our domain, we're going to set the inside greater than 0. So then if we subtract 1 from both sides, or we could add x to both sides, that might be a little bit better. We have 1 is greater than x, but I like to write it with x on the left side. So then our domain is negative infinity comma 1, because x is less than 1. Then our range is negative infinity comma infinity. Our vertical asymptote is going to be x equals negative 1. Sorry, not negative 1, positive 1. Now for the x-intercept, we're going to set this equal to 0. Okay, so we have to get the log by itself. We'll subtract 1 from both sides. So log base 10 of 1 minus x equals negative 1. And I decided to write that 10 in there now so that way we can see that when we change this to exponent form, we get 10 to the negative first power is going to be 1 minus x. 10 to the negative first power is 1 over 10. So 1 over 10 equals 1 minus x. So what we need to do is get this x to be positive. So in order to make that x positive, what I'm going to do is I'm going to multiply everything by negative 1. So negative 1/10 equals negative 1 plus x, and then add 1 to both sides. When we add 1 to both sides, we get negative 1 over 10 plus 1, which I'm going to write as 10 over 10, equals x. So then we get 9 over 10 is equal to x. which makes our intercept 9 over 10, comma, 0. All right, now for our other point. For our other point, we're going to take the inside and set it equal to 1, or you could set it equal to the base. It doesn't matter which one you do. I always like to set it equal to 1 because that will generally make the number smaller. So the inside is 1 minus x. So my other point, 1 minus x is equal to 1. Okay, we subtract 1 from both sides. Negative x is equal to 0, which means x is equal to 0. So then we substitute that back in. So f of 0 is equal to log of 1 minus 0 plus 1, which equals log base 10 of 1 plus 1. Well, we know that log of 1, no matter what the base is, equal to 0. 0 plus 1 is 1. That makes 0, comma 1 our other point. So we're going to go plot those 2 points. 0, comma 1. And 9 over 10, comma 0, which is really close to that asymptote, but not quite there. So that means this function has to go like this. We're going to get really close to that asymptote, but never touch it. All right, now letter D. For letter D, look at that inside now is different. It's not just x, 1x plus or minus a number. We have a linear expression with some coefficients there. So we're going to have to set this greater than 0 to find our domain. Okay, add 2x to both sides. We get 5 is greater than 2x. And then when we divide both sides by 2, we get 5 over 2 is greater than x, which is the same thing as x is less than 5 over 2. So that it means our domain in interval notation is negative infinity, comma 5 over 2. Our range, negative infinity, comma infinity, and our vertical asymptote is x equals 5 over 2. So 5 over 2 is 2.5. Right, so now for our x-intercept, again, we're going to set this equal to 0. So log base 5 of 5 minus 2x plus 1 is equal to 0. We, again, need to make this log by itself, so we're going to subtract 1 from both sides. So log base 5 of 5 minus 2x equals negative 1. So then it's going to be 5 raised to the negative 1 power equals 5 minus 2x. Well, 5 to the negative first power is 1 over 5, which equals 5 minus 2x. And then we have to subtract 5 from both sides. Now when we do this, when I do this, I'm going to change 5 to 25 over 5. So for that common denominator. Right, so then this will get us negative 24 over 5 equals negative 2x. So instead of dividing both sides by negative 2, I'm going to multiply both sides by negative 1/2 because I already have a fraction on the other side. So then that will give me positive 24 over 10 equals x. Well, 24 over 10 can be reduced to 12 over 5. equals x, and as a decimal that is 2.4. So my intercept is 2.4 comma 0. That's my x-intercept. Now for my other point. Again, it doesn't matter which way you do it. I'm going to set the inside equal to 1. So we have, for my other point, 5 minus 2x is equal to 1. Subtract 5 from both sides. Negative 2x equals negative 4. X equals positive 2. Now, if you want to, you can kind of look ahead and say, all right, if I set that inside equal to 5, am I going to get a decimal answer? And if you do, then you may not want to do that. Or in this case, I set the inside equal to 1, and I didn't get a decimal answer. But if I would get a decimal answer, I might want to change my strategy. Again, you don't have to change your strategy. It just makes things a little bit easier. So now I'm going to substitute 2 in. So f of 2 of log base 5 of 5 minus 2 times 2 is 4 plus 1. So then we get log base 5 of 1 plus 1. Well, we know log base 5 of 1, or log with any base of 1, is equal to 0. 0 plus 1 is 1. So 2 comma 1 is my other point. So let's go plot our values. We have 2.4 comma 0, which is really close to 2.5. And then we have 2 comma 1. So our graph will look like this. Now, resist the urge to draw it as a straight line like that. It's going to be curved like the exponential function. All right, the last two here, we have 2 times log base 4 of 6 plus 2x minus 4. Again, our domain, we're going to set that inside equal to 0. It's not equal to 0, greater than 0. So 2x is greater than 6, which makes x is greater than, negative 6. So x is greater than negative 3. Our range is negative infinity comma infinity, and our vertical asymptote is x is equal to negative 3. All right, now we can find our x-intercept. So for our x-intercept, we're going to set this equal to 0. So 2 times log base 4 of 6 plus 2x minus 4 is equal to 0. Now we have to make this get the log by itself. In order to do that, we're going to add 4 to both sides. So we have 2 times the log base 4 of 6 plus 2x equals positive 4. Then divide both sides by positive 2. That gives us log base 4 of 6 plus 2x equals 2. And now we can change it from log form to exponent form. 4 to the second power is equal to 6 plus 2x. 4 squared is 16 equals 6 plus 2x. Minus 6 from both sides, 10 is equal to 2x. And then we get 5 is equal to x once we divide everything by 2. So I'm sure that when you first saw what we were doing, setting that whole nasty log equal to 0, you thought that we were going to get fractions, or that you were unsure what to do. But if we just followed that process, we get our x-intercept, 5, 0. Now for the inside part, again, we can, the other point, we can set the inside equal to 1, or we can set the inside equal to our base, which is 4. Now, again, like I talked about in the previous problem, if we look ahead, all these problems, I set the inside equal to 1, what you can do, but if you set the inside equal to 1, our x value is going to be a decimal, because once we subtract 6 from both sides, we would get 2x equals -5. All right, then we divide both sides and get a decimal. Again, you can do that, but part of this is looking at the problem and strategizing the best way to do this. I'm going to set that equal to the base, which is 4. So other point, we have 6 plus 2x equals 4. 2x is equal to -2, which means x is equal to -1. So then f of -1 is going to equal 2 times log base 4 of 6. 2 times -1 is -2 minus 4. Now the whole point of setting this log, or the inside of the log, equal to 4 is so that way we can use our properties of logs to simplify this. We should put parentheses. I'm going to put parentheses around this 4 so that we know that that -4 is not part of the log. This part right here is equal to 1. So we have 2 times 1 minus 4, which is -2. So -1 comma -2 is our other point. So now let's plot this. 5, 0 and -1 comma -2. And that would be that graph. So as you do more of these, hopefully you're starting to see some shortcuts, and this process isn't taking you as long. All right, our last one here. We have -ln of x plus 1. Now there is no inside number here, so our domain is easy, just x is greater than 0. Because all we have on the inside is x. That plus 1 is on the outside. Our range is -infinity comma infinity. Then our vertical asymptote is x equals 0. Okay, so now we have to find the x-intercept. X-intercept, we're going to set -ln of x plus 1 equal to 0. So then we subtract 1 from both sides. We get -ln of x equals -1. Divide both sides by -1. We get ln of x equals +1. Now we're going to change this from log form to exponent form. So it becomes e to the first power equals x. Well, e to the first power is about 2.7. So our x-intercept is 2.7 comma 0. So understanding these properties of logs is super important in order to do these graphs. So for our other point, we can set the inside equal to 1 and solve, or we can set the inside equal to the base. Now, here's where we kind of want to think ahead again. Because we don't have any inside other than just x, if we set x equal to 1, then that log is going to equal 0, because if we take the log of 1, no matter what the base is, it is equal to 0. So we're going to set x equal to 1. So f of 1 is equal to negative natural log, or ln of 1, plus 1. this part here is equal to 0. So negative 0 plus 1 is 1. So 1 comma 1 is my other point. Okay, so let's plot that. We have 1 comma 1 and 1 comma 1 is up here, and 2.7 comma 0 is about there. So our graph will go like this. So I know that these are more complicated than the exponential graphs that we were doing, but again, once we do more of these, you're going to get the hang of them and recognize the shortcuts that you can take. But you can only really take those shortcuts if you understand your properties of logs. That, the log of 1, no matter what the base is equal to 0. And if I have log base 4 of 4 or log base 6 of 6, that is equal to 1. And that will allow us to get that other point easily. So thanks for watching the video. Make sure to like it and subscribe.